In this video, we're going to take a look at another special type of series, but it's not special in the sense that, as in like the geometric or the telescoping, where we have a very simple procedure for finding the sum of the first n terms of the series, but it's simple in that its convergence can be easily determined, right? So we can answer our first question about the convergence of the series quite easily, and that's what we're going to develop in this video. But it's not quite as easy to answer the question about, okay, when we know it converges, what number does it converge to? In some sense, we have a partial answer to that question, and again, that's something that is usually discussed in a more advanced course. So first, we're going to talk about like what a p-series is, and then we're going to see how could we possibly determine when a p-series converges, right? So let's define what a p-series is. So a p-series is one of the form, right? So it's an infinite series, and it typically, again, kind of in a standard way, it's defined k going from 1 to infinity, and the function now that we're summing up is 1 over k to the pth power, right? Where p is a real constant, right? So just to kind of give you an idea of what it looks like. I mean, it's certainly not super complicated, but let's say, here are just some examples of a p-series starting at k equals 1. Let's say you have just, 1 over k. So what if p is equal to 1? Then you end up with 1 plus 1/2 plus 1/3 plus 1/4, and so on. So that's what it looks like when p is equal to 1. You can have any power of p there. The question is going to be, for what values of p, if any, does it converge, right? Let's say you could have p being 1/2. And essentially, then that would be like taking the square root of your positive integer, so you'd end up with 1, and then plus 1 over the square root of 2, plus 1 over the square root of 3, plus, I'll write it in its unsimplified form, 1 over the square root of 4, and so on, right? So that's p-series. And it's a nice series because, again, the fact about its convergence is quite easily established. In fact, what we get to do is we get to apply our integral test to see how this works. And the reason why the integral test works is because these functions are fairly easy to integrate, right? So let's do that. So to determine the convergence of a p-series, we will apply the integral test. All right, so then what are we going to integrate? Well, we're going to consider the corresponding improper integral, and I'll go from 1 to infinity, and we're going to look at the function 1 over x to the p, right? So that's what we're going to look at and see if we can determine what has to be true for this integral to converge. So first, as usual, let's set up our area function. So we're going to integrate from 1 to b. And to integrate this, since it's really just a power function, right? We're going to rewrite this and write this as x to the negative p dx. And since it's a power function, we get to apply our power rule for antiderivative. So we're going to add 1 to the power. So we're going to have x to the negative p plus 1. And then we're going to divide by negative p plus 1. And we're going to evaluate that at 1 and at b. So we're going to plug in the b for x. So we will have, and let me put the 1 over negative p plus 1, that fraction. I'll just kind of pull that out. And then let's replace the x with the b. So we'll have b to the negative p plus 1. And then we're going to have minus 1 to the negative p plus 1. Well, 1 to any finite number, and again, p is a real number, so negative p plus 1 is a real number. 1 raised to any real number is 1. So I can simplify that just a little bit, and I'll have 1 over negative p plus 1 times the quantity b to the negative p plus 1 minus 1. All right? So now we're going to have to decide what's going to happen to this thing when b goes to infinity. All right? So let's see. So we're going to take the limit as b goes to infinity of 1 over negative p plus 1 times the quantity b minus p plus 1 minus 1. Right? Now, this factor here does not involve b. So we treat it like it is. It's a constant. So we can pull that further out. In fact, let's do that. So again, just to kind of simplify what we're really looking at. So we'll have our constant in front of our limit now, and we're taking the limit as b goes to infinity. B goes to infinity of b to the negative p plus 1 minus 1. Now, what's going to happen is if you think about this, we have b raised to some power. If that power happens to be negative, then remember what would happen is we would end up having the reciprocal, which would put the b in the denominator, right? And then we would have like 1 over, and then we would have b, and then that b would be going to positive infinity. So if the negative p plus 1 is less than 0, right? So if this quantity is less than 0, then we know that this thing is going to converge, right? It's like having, as an example, like if you have, not p, but let me write the b. So for instance, let's say we have something like this. B goes to infinity. If I have b to the negative 2, for instance, then that allows me to take the reciprocal, right, which we've done quite a bit. And then, yeah, so now I would know that this thing converges to 0, right? Whereas if I have something positive up there, then I won't take the reciprocal, and then it would just keep getting bigger and bigger and bigger. So this limit, or let's say, yeah, this limit converges right, if negative p plus 1 is a negative number. But then if I solve this for p, let's say I subtract 1 from both sides. So I get negative p is less than negative 1. And then to isolate the p, if I multiply this inequality by negative 1, then I have to change the direction of the inequality. So therefore, p is greater than 1. So what this argument shows is that if p is greater than 1, right, then my improper integral will converge. Otherwise, it will diverge. And you can see, for instance, if P is equal to 1, then look at what happens. You end up with negative 1 plus 0 in the denominator over here. That doesn't work, right? So it converges if P is strictly greater than 1, and it diverges if P is less than or equal to 1. And that essentially is what we call the P-series test, right? So let's just kind of summarize that and see where we go after that. So this is our theorem, and this is our P-series test. And I'll just make it a nice short one-liner. So our P-series, okay, going from 1 to infinity, 1 over k to the p, this one converges if p is greater than 1 and diverges if p is less than or equal to 1. All right? And so again, the test, so in terms of one of these special ones, it's along the same lines as the geometric in terms of its simplicity. Just looking at a specific number, you can identify if the series converges or not, right? So I'll just do a couple examples here, and then there's just one special thing we want to mention. So, for instance, if we have something like this, right? Oh, nope, this is K, not P. So here's our P series. It's the sum of K, with K going from 1 to infinity, of 1 over K to the 1.01. So I made it just a little bit bigger than 1, and that's all we need. So in this case, our P is 1.01, which is bigger than 1. Therefore, our series converges. Right? If, however, and so in a lot of these problems, if you have to do much work, it's probably just a bit of algebra, maybe, just to kind of simplify things. So let's say you had something like this, right? Where your expression is not in that standard form. Very similar to what we had to do for the geometric series when the expression was a little bit more complicated. It's something similar here, right? Well, let's see if we can rewrite this and get it in that particular form. So, okay, going from 1 to infinity. Now, so since we need to have all the k's in the denominator, so I'm going to take the reciprocal of this one and write it as k to the negative 4. And then this one, let's write it as a fractional power. So this will be k to the 6/5. Properties of exponents, we add those. So we have the sum, k going from 1 to infinity. We have 1 over, so adding those exponents, so negative 4 is the same as negative 20 over 5. And then adding 6, that gives me k to the negative 14 over 5. So if we were asked to identify the p, right, then we would want to go through this particular process. Then we would see that p is equal to negative 14 over 5, which is less than or equal to 1. And because of that, by our test, so in this case, the series diverges. Right? So again, very easy test to apply, right? But in the case where it converges, we don't always know. There are some values of p for which we know what it converges to. In fact, when p is a positive even integer, there are lots of interesting formulas that you get. But in general, we don't know. So for instance, this one right here, this 1 over k to the 1.01, we don't know what it converges to, but we just know that it does converge. Right? Now, there is a special case of the p-series that is worth mentioning, and that's when p is equal to 1. So right at that cutoff point, right? So when p is equal to 1, we get what's called the harmonic series. Right? It looks like this. And in fact, it's one of the ones that I wrote down earlier, where it's simply, in fact, let me write it down again so we can see in all its glory, and now that we know its name, the harmonic series. So it's 1 plus 1/2 plus 1/3 plus 1/4 and so forth. And I mean, there are lots of reasons why it's called a harmonic series. A lot of it has to do with not like formal music theory, but more like the physics of sound, like acoustics and things like that. But basically, um, when you look at like a vibrating string, like you pluck the string of a violin or a cello, and it vibrates, then it has associated overtones, right? When you look at the wavelength of those overtones, they end up being 1/2, 1/3, 1/4, etc. So everything but the first one, right? So again, when you look at like the physics of sound and so forth, you end up using the harmonic series, or you recognize these terms showing up quite a bit. There's also another interesting thing regarding the name harmonic. When people think about a mean or an average, they're usually thinking of specifically an arithmetic mean. So an arithmetic mean is your regular average, where if you have a set of numbers, you add them up, and then you divide by however many numbers are there. So this is your arithmetic mean, right? There is something referred to as the harmonic mean. There's that, again, that wonderfully sounding word. So the harmonic mean. What does it do? Well, there the numbers have to be non-zero, right? Because this is what you're going to do. To find the harmonic mean of a set of numbers, you first take the reciprocal of the numbers. So 1 over x1 plus 1 over x2 plus dot 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 1 over xn, right? So you take the reciprocal of the numbers. That's why they need to be non-zero. Then you take the arithmetic mean of those reciprocals, so divided by n, and then you take the reciprocal of the answer. Quite the process, right? And again, it's another way of computing a mean, right? It's not the arithmetic mean, it's the harmonic mean. Well, it turns out that the terms in your harmonic sequence, so if I just look at so here's the harmonic sequence now. If I just write it down where I don't add them up, so if I take my harmonic sequence, I'll have the terms 1, 1/2, 1/3, 1/4, 1/5, 1/6, etc. And if I take out the 1, so if I look at a pure proper fraction, if I take out the 1, it turns out that the I don't need to take out the 1. I just have to say this. Oh, now I'm getting all messy. But let me say this. So let's leave the 1 in there. If you take any of the numbers subsequent to 1, like so if you take 1/2, it turns out it is always going to be the harmonic mean of the two surrounding numbers. So just to illustrate like how you actually compute the harmonic mean, let's find the harmonic mean of 1 and 1/3, and let's show that we get 1/2. And that's true about any of these numbers, right? So let's compute the harmonic mean of 1 and 1/3. So the harmonic mean of 1 and 1/3 is, well, let's see, let's do the process. So it says we have to take the reciprocal of the numbers. So the reciprocal of 1 is still 1. Then we take the reciprocal of the 1/3, which is 3, add them together, average these two, and then take the reciprocal of the arithmetic average, right? So what would that be? Well, that's 4/2 to the -1, so that's 2 to the -1. And look at that, we end up with 1/2, the one that's smack dab in the middle. And it's true about all the other ones, right? So if I take the harmonic mean of 1/2 and 1/4, I will get 1/3, right? So the word harmonic means a lot. You know, like I said, it shows up like in the wavelengths of the overtones of a vibrating string. It shows up in other ways of averaging things. So this idea of reciprocals of just your positive integers is very, very important, right? So so kind of, just in summary, as far as what we're, really focused on is the fact that we can now analyze p-series, and a special case of the p-series is the harmonic series that happens to diverge. So don't be shocked if sometime in the future you encounter something that has to do, something that is harmonic. I'm not just talking about the stuff that's in your playlist. Well, I will see you in the next video.